Hello, AP Physics. In a way, this is a little test video. I'll fill you in a little bit. Maybe I'll even teach something a little bit for a few minutes. I don't know. We're going to make the best of this. It's a strange situation, obviously. I'm going to let you see your room one more time. I don't know if we'll be back or not. I've just found out that basically the building is going to be locked down. Let me just at least touch base. I'll be giving homework assignments. You can write them by hand, take pictures of them, send them to me. One possibility is just simply email or sharing, on Google Drive or whatever. But I may also try to set up PowerSchool so you can upload the images to that. So we'll be continuing that. Thankfully, you've got a good textbook. That'll help us a good bit. It does have more sometimes than we need, so we need to trim that down. Obviously, what we're doing right now is current. And I remember, I guess it was a few days ago, we started drawing symbolically circuits like that, battery to resistor. We learned Ohm's law. One thing I remember talking about was whether or not that's just redundant or self-referential, circular definition thing. So resistance is the ratio of voltage to current. Is that all it is? Is it just some letters defined in terms of each other? No, because they're connected to other things. And the thing that makes resistance real is that there really are things called resistors that have fairly stable amounts of resistance. Now, since I won't have access to the room, it might be a little bit limited in what I can show you, but one of the questions that's going to come up is basically, is Ohm's law true? Well, it is by definition. If you define R to be the ratio of V to I, then of course it's true. How can it not be? The question is, if you actually have a real resistor and you apply different potential differences across it, will it produce currents that fit this law? Is the current really going to be directly proportional to voltage? That's something we've done a lab in the past on that. I'm not sure how that's going to work out. Maybe I'll take some stuff home with me. I got to get a box out. But that's one of the questions. And then there's going to be this whole issue, which I think most of you, not all of you, most of you had AP Physics 1 last year. And I think they just touched on some of this. I think maybe you did learn about resistors in series and how resistors in series add up to make an effective resistance. You just add them, like R effective equals R1 plus R2 plus however many there are. And it's kind of like having to run through successive obstacle courses. I guess that slows everybody down. I'm not sure the analogy is perfect, but it's not too surprising if you are being forced to go through two successive resistors, that's more resistance. We could talk more about just exactly how that works at some point. Then there's also the question about resistors being in parallel. Now, the grocery stores are pretty packed about now. And say there's a long line of people moving very slowly trying to get the last thing of toilet paper or Purell that I haven't been able to find. So what if you open up another register? Doesn't that increase the flow of traffic? Now you can have traffic going through both checkout lines. And when you go through both checkout lines, that makes everything easier, lets the traffic flow more quickly through the store. And remember, with capacitors, when you had them in series, you did the 1 over thing. That's what happens here when these resistors are in parallel. 1 over the R effective. Now this again is for series. If they're in parallel, it's like 1 over R1 plus 1 over R2, etc. Maybe you knew that. A lot of your homework that I already assigned from chapter 25 is this sort of thing where you're given these circuits, and sometimes there's lots more resistors, and you find the current in each one, you find the voltage across each one. We need to talk more about that and do some examples. There's also something that I'm going to go ahead and mention right now called Kirchhoff's rules. These these branched resistor problems, with parallel and series, it's kind of like parentheses logically. You should do these first, and then when you get that done, then that's in series with that. People pick that up very quickly. It's pretty easy. However, I can throw a very bad wrench into this problem, make it a lot harder. If I do something like put another battery right here, now all your little rules about series and parallel don't quite make as much sense anymore. And the way we solve this is with Kirchhoff's rules. There's two very simple ones. There's the junction rule. And the junction rule is the one that basically says any current flowing into a junction has to flow out. So for example, if this current is called I1, this could be I2, and this could be I3. Look at the way they're defined. I1 is flowing in, I1 and I2 are both flowing out of that junction. Clearly, conservation of charge doesn't have to add up. So here I1 equals I2 plus I3, kind of obviously, just like any kind of traffic would have to do. There's also the loop rule. I'll tell a quick story here. Twice in my life, I have been talking to different people about running a course to go for a run. And in each case, it was a loop that came back to where it started. And there were hills. And I remember the discussions of which way we wanted to go. And each time, two different people, years apart, each said, let's go this way. It's more downhill this way. No. If you come back to the same point, you went up just as much as you went down. Maybe the hills were steeper in one direction and less steep in the other. And I don't know whether they wanted to run up the steep ones and down the gentle ones, or up the gentle ones and down the steep ones. I'm not sure what the preference was. But it was clear talking to each of these people that they didn't really get it, that the elevation changes have to add up to zero. If you run all the way around the course, come back where you started, if you did a total of 50 meters of dropping, you also went 50 meters up because you're back at the same level again. Now, I think you understand that. How does it apply here? What you do to do the loop rule is you start somewhere, anywhere you like, anywhere on the course. And anytime you go from the negative side of a battery to the positive side of the battery, you just went up. So here we went up, and I'm going to use electromotive force symbol like E1 for that. I'll call this one E2. So you go up E1, then you come around and you go, let's call this R1. You go down I1, R1, like you had to go down a staircase or something. You always drop when you go with the flow of the current across the resistor. And then if I got to this place, I go down E2. If this is the route I choose, like this, go down E2. I guess I call this I2. I call this R2. I go down I2, R2. And now I'm back down this level from here on equals 0. That's an example of the loop rule. And the idea is you write the loop rule for different ways of running the course. And then you end up with a set of equations, a system of equations. And the question is, how do you solve that? There's lots of ways to do that. Probably won't get into that right now. But we do need to talk a little bit more later about how to use Kirchhoff's rules. I think the next time you see me, it's going to be from my house. And I'm going to have probably a much smaller board to write on. I do have some kind of little whiteboards. I'll take some markers home. I may even take some meters home so we can learn how to use a multimeter, video in my house. But whatever we can do, we're going to make the best of it. By the way, I was hearing a little bit in the meeting this morning about, the College Board. We don't know what's going to happen with the AP test. We don't know if they're going to give them on time, let schools have them take them late, do a makeup thing in July. Nobody knows right now, but we'll learn what we can and try to do it pretty much on time. So until next time, which should be very soon, we'll see you later. Bye.